Yeah, thank you very much. Dear colleagues, ladies and gentlemen, sorry that I cannot give this presentation in Thai language. I think one of my biggest mistakes in my life was that I started with English and not with Thai language. But, I hope we will manage it. I don't think you will find too many Germans outside of Germany because tomorrow the soccer World Cup starts. And I do not think that Germany will be a successful team. I decided to come over here to do this lecture today. It's a great honor and also a great pleasure for me to give this penetration on microwave and radio frequency application in agriculture here at this conference. The idea for the lecture was born in March on my last visit to PHTI. This visit stands in a long tradition of relations between my university and Chiang Mai University. I guess it is a good symbol that this conference takes place during the festival of your King's 60 years crowning ceremony. I think also due to your Majesty's enforcement, colleagues from my faculty brought trouts to northern Thailand and made successful research together with the aquaculture and animal husbandry scientists here in Chiang Mai. So it is possible to produce trouts in large quantity here in this region, and I know that your king likes them very much. In this good old tradition, I'm also here today and try to realize a successful research cooperation together with the colleagues from PHTI, namely Dr. Vijen and Dr. Vicha, especially in the field of radio frequency and microwave application. And during my presentation you will see that we have perhaps several opportunities to work in this field in the use of microwave and radio frequency energy for treatment of plant materials. After a short introduction, I will bore you perhaps, but I don't think it's boring, with the theoretical fundamentals of this technology. And then I will give you some results of experiments we did, especially concerning microwave but also radio frequency application. And then I will show you that this is not a new technology, that we have this technology especially in industrial applications, but not in the field of agriculture. And I will close my lecture with some conclusions on the topic. This is perhaps one important thing. This is the frequency spectrum, and I want just to explain what microwave and radio frequency is. Don't be angry, this is the only German slide I have, but I did not translate it because you can everything, it's self-explaining when you look on the right side of the slide. Everything is explained. So microwave and radio frequency are electromagnetic waves, like other electromagnetic waves, for example, the light here in the room or the frequency. Also, that you can hear me, it's also a matter of electromagnetic waves. But these waves which you can hear are in the spectrum above here, and they are not in this region. We are looking on high frequency, and the high frequency spectrum in the electromagnetic frequency spectrum is between 300 gigahertz and perhaps 30 to 300 kilohertz. And this is the frequency spectrum, and perhaps there is one important thing which you have to keep in mind to understand what I explain later. The higher the frequency is increasing in this direction. The higher the frequency, the lower the wavelengths. You see here, when we have high frequencies, we have low wavelengths. In the case of microwaves, for example, the wavelength ranges between 1 millimeter and perhaps 100 or 1000 millimeters. perhaps 1 meter is normally radio frequency, high frequency in the case of radio frequency, and the difference between radio frequency and microwave is mainly the wavelengths. Whereas radio frequency we have higher wavelengths, and this has a key effect on the use of this kind of waves. And in the case of microwaves we have shorter wavelengths but higher frequencies. And you see that we are using microwaves, especially microwaves, in different fields of applications. Everybody, perhaps not here in Thailand, but because you have not so many fast food than we have in Europe and in the United States, but we use microwaves I think nearly every day in our households. But you have microwaves also in your handy, in your mobile phone. In Germany we call it handy. This is a mobile phone, and you see that the mobile phone is ranging between the frequency spectrum of radio frequency, which is in here, and the frequency spectrum of microwave, which is here. And this is threatening the industrial applications, because these frequencies, which you can also, or you could possibly use for heating purposes, these frequencies are closed for heating purposes because we use them in the mobile phone technology. On the other hand, mobile phone technology is widespread, it's mass production, and this is the reason why the electrical implements are becoming more and more cheap and therefore interesting for other applications. Radar, for example, is also a typical application of microwaves and radio frequency. So the difference between both is the frequency. The higher frequency is microwave, the lower frequency radio frequency. On the other hand, in the case of radio frequency we have higher and longer waves, bigger wavelengths, and smaller wavelengths in the case of microwave energy. Now the question is, what does happen when you use this kind of energy? We are not interested in broadcasting. We are not interested in broadcasting. Perhaps in a special way of this technology we are also interested in broadcasting. That is radio frequency identification, RFID technology. This technology is a key technology in the traceability of products from farm gates to market. In this case we are more interested in broadcasting, but in our special view today we are looking only on the heat transfer, which is possible by using this kind of energy. And now the question is, how does it work? The conversion of microwaves and radio frequency into heat. This is shown here. Here you can see a water molecule. A water molecule working on the slide here. And what is shown here? If you look onto special dielectric materials, they normally consist of ions or molecules, and especially we are interested in those molecules which dipole character. One of the most important molecules with dipole character is water. It's the water molecule. As we have no ions in our agricultural materials, the ionic polarization and orientation in an electromagnetic field is not important for us. So we can leave out the left side of the slide and just look on the right side. And here you have a water molecule, and what is happening when a water molecule is brought into an electric field? You have an electric field, and when this electric field is working on the water dipole, the water is orientated in the direction of the electric field, plus to minus, minus to plus. If you have a stable electric field, nothing will happen. The orientation happens, and afterwards the process ends. But in the case of microwave energy, we do another thing. We change the electric field, which is shown here by this by this symbol. You can see by this arrow, you can see that this field is changing. In the case of microwave, of a typical household microwave oven, this is changing 2.45 billion times per second. So fast that you would not be able to look on it. 2.45 billion times per second. This is so fast that the water molecule cannot follow this change of the direction. It follows it, but not so fast as it is done. And this is not the only, this is a water molecule. Here you have two hydrogens, one oxygen. This water molecule is now working in the electric field when the electric field direction changes. And this is not only one water molecule. You must perhaps think that there are several billion of water molecules now doing the same. And they have no space to do this. And what's happening? You get friction between different water molecules. And this friction causes heat. And makes the material and the water warm. This is the typical way how water works, if it can work, if it is free to move. And there is one special case where microwave energy and electromagnetic energy cannot have any effect on water. This is when the water is bound. And the typical case for this is bound water in ice. If you have frozen water, this movement cannot happen because the water is fixed in its position. The depots are fixed in their position, and therefore it is useless to put some ice into a microwave oven. You will not be able to heat this ice. Or if some water is melting on top of the ice, you get the phenomenon that some water, the not bound water, is cooking on the ice. You can cook on the ice by use of microwave, and the reason is that bound water cannot move. And we have the same in our agricultural products. You know that water is not only free in the products, you have also bound water in your agricultural material. So if the water is in a very strong binding surroundings in the product, you will not have any movement, and then electromagnetic energy cannot cause any effect. But normally we have an effect. And the conversion of energy can be described with this equation. This equation shows how much power is set free, how much electromagnetic power is set free in a product by use of microwave or radio frequency. And you see that we have two factors, E square and F, which are influenced by the technical equipment, and the other two factors, epsilon 0 and epsilon R2, are affected only by the material. So the material decides how microwaves work in the material, and from the technical point of view we have two possibilities to influence the power and the capacity of the electromagnetic field. This is E square and F. E square, the electric field strength, is given by the system. You have to calculate it very severe, because if you provide very high electric field strengths, you get lightning in a microwave system. You get lightning, and in consequence of the lightning, the product burns. So you have to be very careful in changing this, but this is quite easy. The bigger the cavity, the lower the electrical field strength, and if you have a big cavity, nothing can happen. Therefore, if you buy a microwave oven, please buy one with a high volume, then you get a low electric field strength and a very homogeneous field. A small one is more difficult. On the other hand, we can use the frequency to get a higher electric power supply and heat transfer to the product. And this is the reason, we can go back here to this picture, why the mobile phone people always try to raise their frequency. They started here and now they are here in the E and UMTS and so on frequency area, and this is the way how they can get more power to the mobile phones. They cannot do this one, otherwise you will perhaps inflame your ear or something like this. So the only possibility for them is to raise the frequency. These factors come from the product, and one of the most important factors is epsilon R. Epsilon R is what we call the dielectric loss factor. You may perhaps wonder why we say this is a loss factor, because it is very important for us. The higher it is, the more heat we get, but this is the interpretation of an agricultural engineer, as I am. Those people who found out this basics are broadcasting engineers, and they are not interested in losing electromagnetic fields and power. They want to keep it work, because then they could broadcast over a wider range of areas. In their case, this is really a loss, but in our case, it is exactly what we want. The higher the loss factor, the more energy is attenuated in the product, and so we try to get energy in the product. But this has consequences, and I will show these consequences immediately. If you look in the way how microwaves and also radio frequency waves enter dielectric materials, like an agricultural product, can be a fruit, can be wheat or something like this, a potato. We will have a clear look on potatoes future. You will see that the way how the microwave energy penetrates the product is following the slope of a 1 through E function, of an exponential function. And if you divide 1 through the Euler number, you get the exact result of 0.37 or 37% of the weight of the value here at the surface of the material. This is E0. This is the go back here. This is the electric field strength on top of the material, and the active penetration depth is restricted up to or down to 37% of E0 here at the surface. This is the active penetration depth, and the effective penetration depth here is shown in a mathematical calculation. And now you can see some interesting things. The higher the frequency and the higher the wavelength, the lower the frequency, the higher the penetration depth. And the higher epsilon R, the higher epsilon R, the lower the penetration depth. And you can see this here. We have here the calculated penetration depth of different materials, and I will start perhaps with water. You see, water at the temperature of 25 degrees centigrade, water has a very high epsilon 2, and therefore the penetration depth in water is only 1.4 centimeters. If we change to, for example, Teflon, which is a very proven material to use in a microwave oven because it does not absorb microwave energy, Teflon has very low epsilon 2, and therefore we have a high penetration depth. And if you look in agricultural material, for example, bread, you have 2 to 5 centimeters penetration depth with microwaves. Potatoes only nearly 1 centimeter. Mashed potatoes, perhaps 80 millimeters or something like this. Peas, carrots, 1 centimeter. Meat, about 1 centimeter. Paper, 20 to 60 centimeters. Wood, up to 350 centimeters, and so on. And this is a clear sign that if you do not slice the material into certain geometries, you will not have any chance to get microwave energy into the product. Or you have to change the kind of energy and to go to a kind of energy with a higher wavelength. And this energy with a higher wavelength, here you see the wavelengths of several meters compared to microwaves with several centimeters. Here we have several meters of wavelengths, and therefore theoretically with high frequency, this is the frequency with lower frequency than microwaves, but higher wavelengths than microwaves, you have higher penetration depths. These are the penetration depths for microwaves, and you see when we have ice, for example, ice is not absorbing microwave energy as I described before, and therefore we have high penetration depths into ice. But if the ice is melting, if the dipole character is able to move the dipoles in the electric field, the electric energy is absorbed, attenuated in the product, and the penetration depth goes down. This is very important to keep this in mind, otherwise you cannot